Hi, I'm Martin, and this video is about symmetric relationships between isomers. You've probably heard about these between molecules, but very similar relationships exist between molecular fragments as well. Let's look at symmetry for entire molecules first. Two isomeric molecules, that is, two molecules with the same chemical formula, can have symmetry relationships. To determine the relationship, we ask ourselves a series of questions about the molecules. The first question is whether or not they can be superimposed onto each other. If they can be rotated or moved in such a way that they match perfectly, then they're the same molecule. But if they're not identical, then we ask, are they mirror images of each other? If that's the case, then the two molecules are enantiomers. This is most easily identified if the molecule has a single chiral center. The example shows a trisubstituted methane, where all four bonds bind something different. Then it's easy to see that they're mirror images of each other. But if they are not mirror images of each other, then we have something called symmetry non-equivalent. Then we ask, do all the atoms in a molecule have the same constitution? That is, do they all have the same connectivity as the other molecules? When this is the case, they're called diastereomers. These two molecules are diastereomers. Finally, if the molecules don't have the same constitution, then they're constitutional isomers of each other, such as these two disubstituted benzene rings. Now over to molecular fragments. They're pretty much the same thing as molecules, but focusing on two isomeric molecular fragments. It can be a single atom, or a cluster of atoms, or even a phase of the molecule, as long as they're isomeric within the same molecule. We again ask ourselves a series of questions to determine what the fragments are to each other. The example I'm going to use for this is a molecule called norbornane, and we will be focusing on the hydrogens of the molecule. The first question we ask is if the molecule has an n-fold rotational axis, such that our two molecular fragments end up superimposing. If we do, then the two fragments are homotopic. In the example, we have sets of two hydrogens which are homotopic to each other. These are on the top of the molecule and on each side, connected by a C2 axis. If the fragments cannot be superimposed by an axis of rotation, then they're heterotopic. But we don't stop there. The next question we ask are if they are separated with a mirror or an improper axis of rotation within the molecule. If they are, then they're enantiotopic, such as these two hydrogens or these two hydrogens. Then, if they're not related by either an axis of rotation or improper rotation, we have to ask ourselves, do they have the same connectivity? If they do, then they're called diastereotopic, such as these two hydrogens on the norbornane. But if they don't have the same connectivity, we have arrived at two constitutionally heterotopic molecular fragments. That is, two fragments who aren't related by any symmetry at all, such as these two. If you thought that was too hard, but you've mastered the molecular isometric symmetry, there are other ways of figuring out the molecular fragment symmetries. We can use the substitution criteria. That is, you consider replacing one of the fragments at a time and comparing the symmetries of the two molecules you get. If replacing either or leads to the same molecule, then the two fragments are homotopic. Replacing enantiotopic fragments lead to enantiomers. Replacing diastereotopic fragments lead to diastereomers. And replacing constitutionally heterotopic fragments lead to constitutional isomers. Now, why does the molecular fragment symmetry matter? Other than having a precise way of describing molecular symmetry, it matters because, for example, enantiotopic fragments behave different in chiral or achiral environments, which can be important for things like NMR spectra. If you got two enantiotopic hydrogens, you'd often expect them to have the same proton NMR signal, but they might not. They might produce slightly different signals depending on which solvent you use. Chiral solvents, or chiral environments in general, can give rise to different NMR signals for these enantiotopic fragments.